We have a quadrature encoder. You see these nicely spaced slots here. I think there's 72 of them in a full circle. And what we have is two outputs on this guy. We have analog, I think is the one on the bottom, and digital is the one on the top. So analog is the output from the phototransistors, and it happens to look sinusoidal, which means we could probably get some more resolution than just that 72. Digital quadrature generally can multiply that by 4 because of the different transitions, but with this new thing I'm working on called anaQuad, that's analog quadrature, I'm able to multiply that by 4, so I can get 16 different positions for every slot on this encoder disk. So here on the display down here we have two different numbers on the right side. The top number is the anaQuad number, which is about 4 times higher than the one below it, which is the digital quadrature output. Here on the scope is the 2 channels in quadrature. It's very hard to move this disc this slowly, but we're doing it. And you can see the anaQuad number increasing quite a bit. So there it is. Now I've optimized this code a bit so that it actually runs almost as fast as the digital quadrature decoding. Uses a similar switch statement, and what it does is it looks for crossovers between various multiples of the 2 input signals. So here I'll take a look at that over here. So you see these are the 2 quadrature input signals, and we can invert it. So if this is channel A, this is inverted channel A. If this is channel B, this is inverted channel B. Then we also have double channel B and double channel A. And so each of these crossovers is a discernible point in the this represents one single slot on the encoder disk. So we've got a crossover here, and here, and here, and here, and here, and I guess I might as well go through them all. There's another one, and another one, and another one, and another one. Did I miss one? There's another one, and one down here, and one over there. So that gives us 16 discernible points between one slot. So that means that we should be able to get 16 times the resolution of that really low resolution optical encoder disk. So if I rotate that one full cycle, let's see, right now the 72 marking is right there, and this hole is down, and we're at 140 and 35. So if I rotate that one full cycle, there we go, that should be about one full cycle. Now we're at 1,200 and something and 320 or something like that. So that sounds about right. So I did the calculations, and I think I should get about 1,100 counts per revolution. I can go back and forth, so it can go either way. It goes up and down. I can go really slow. You can definitely see the analog value is increasing faster or more often than the digital value. Oh, I guess I'm decreasing. Can also go really fast, and this sometimes causes some trouble, so let's see what happens. Electrical noise interferes with the... Whoa, wait a minute, it's not moving yet. Oh, it is moving. Hey, look, it's spinning, and all I'm doing is holding its input. Okay, well, that's fine. Okay, it's not going full speed, so that's even better. Guess some 60 hertz noise is causing it to do its thing. Alright, so there you go. Now it's increasing. The scope might not be a very reliable thing to look at that low speed because you get some aliasing, so let's speed it up here. Alright, this is full speed. I don't think we're getting any aliasing now. Let's see. We might have a trigger problem, however. There we go. Alright, so you can see it's counting. It's doing its thing. You can see on the scope, interestingly, the two channels have changed in magnitude a little bit. And I think that has something to do with the values of the resistances used. I can come back to that, but anyways, you can see that when it stopped, and of course, let's go back to scroll, turn off that trigger. Alright, you can see when it stopped and it's going really slowly, it looks like they both go all the way down to ground, although their amplitudes are slightly different. One of the things about anaQuad, because it's looking for my asleep screen, because it's looking for these crossovers here, it shouldn't matter too much whether, say, the amplitude of one is slightly lower than expected or higher, or if maybe there's a slight offset. That's kind of the whole point of using this crossover detection instead of using thresholding. Because, obviously I could set a threshold here, but what happens then when this amplitude is only that high? You'd never get there. So that's kind of the point here, which you could see with that. Oh, and like I said, sometimes when you run the motor, it interferes with the display. Got some really long antennas here that can pick up some electrical noise, so I can't look at that display right now. But what I was going to show you was these two have differing amplitudes, slightly different, and it did until it crashed. Still function. Is it still functioning? No. But anyways, you get the idea. I think it's pretty cool. It uses a whole bunch of switch statements to detect each one of those crossovers. But the cool thing about switch statements is they are pretty quick compared to, say, using something like... maybe I'm mistaken, but I think Arctan, in a case like this, probably wouldn't work too well. Because, look, those two amplitudes are slightly different. So, I think it's pretty cool. I think it's pretty badass to be able to get 1,100 discernible points with something that you can easily see with your eye, how big those slots are. It may not be perfect, but it's pretty cool.